Alright, here we go with Chapter 9, Homework 1 review, first of two assignments on this last chapter that we're covering. Average this week was 9.75 out of 12, which is pretty good, a little bit higher than last year, so we do seem to be hitting our stride at the last time. Let's just hope that this continues on into the exam that we have this week and next. Alright, so the first question here deals with counting ions in a crystalline, ionic crystalline solid. This topic, just to make sure we're clear, is not going to actually be covered until the final. So this is a little bit ahead of where we are for examinations, but you will have to see questions like this on the final exam. So we have an ionic crystalline solid MX2. I should say also these first few questions are requests from students. The last few are going to be ones that I thought we didn't do as well on as some of the others, so I'll go through sort of a variety of these. Alright, so the first one, as I said, not relevant for this week's exam, but will be on the final. So you have a crystalline solid MX2, that's the chemical formula. And we want to know which of the following arrangements of ions is consistent with the stoichiometry. So this is really, again, using the rules that we learned for counting different positions in a cubic unit cell and figuring out which ones of these gives us the correct ratio of MX2 as the empirical formula. So for choice A, we're going to go through all of these one by one. We have M2 plus ions at the corners and the faces. So for M2 plus, we have ions at the corners. There's going to be 8 corners in a cube, and those are each going to count as 1/8. So each corner position is shared by 8 adjacent unit cells, so they count as 1/8 each. So that's how we count our corner positions. And then we have each face also has one. So there's 6 faces in a cube, and each of those is shared by 2 unit cells. So we're going to count those as 6 times a half for the faces. So just like any face-centered cubic arrangement, we have 4 of those in the unit cell. Then if we go to X minus, we say that we have 8 X minus ions at the tetrahedral centers. So we have 8 tetrahedral centers. Each of those counts as a full ion because the tetrahedral holes are inside of the unit cell. So in this case, we have 8 of those. So the formula then of this compound, we have 4 M's. We have 8 X's, which means the empirical formula is MX2, which is the correct formula for this compound. So we think that choice A is going to be the correct one because it gives us the same chemical formula. So we'll pick that one. Let's verify that the other ones don't work out. So if we go to choice B here, we have M2 plus ions at each face. So this time we have 6 faces all occupied, which is going to be 3 M2 pluses, X minus ions at the corners. So if X minus is at the corners, we would have 8 corners as 1/8, and that's going to give us just 1 X minus. So this formula would give us M3X, which is not the correct formula, because we get 3 metals, 1 nonmetal. Alright, and then if we go to choice C here, we have M2 plus ions at the corner. So if we go to M2 plus, we have 8 times 1/8 for M2 plus. We have 1 M2 plus, and we have X minus ions at the faces. So that's going to be 6 faces counting as a half each for X minus, plus 2 at the tetrahedral center. So that's going to be 2 tetrahedral centers counting individually, which is a total of 3 plus 2, which is 5. So this would give us MX5, which is also not the correct formula. And then choice D, we have 4 M2 plus ions at the body center. So anything that's inside and in a body-centered position just counts as 1. It's not on the edge of the unit cell, so it doesn't get shared with any. And that was going to give us 4 M2 pluses. And then for X minus, we say corners and faces. So at the corners and at the faces, we would have 8 times 1/8 for the corners, and then 6 faces counting as a half, which gives us, again, 4. So this would give us M4, X4, or MX, also the wrong formula. And then choice E, we have M2 plus ions at the corners and at the faces. So that, again, is going to be 8 corners counting as 1/8 each, plus 6 faces counting as 1/2 each, so a total of 4. And then we have 4 X minus ions at the octahedral centers. This one's a little bit ambiguous because there's octahedral centers both in the center and on the edges, so I don't really like how this answer choice is worded, to be honest with you, but even if we count those as a total of 4, none of them are shared, that's still only going to give us M4, X4, or MX. So it doesn't really matter which of the octahedral holes are actually occupied, because even at the most you're going to only have 4 X minuses with your 4 X's, and that's not the correct formula. So So what we wanted to do was find which of these arrangements gave us the correct formula mx2. It was only the first one, so that's going to be our answer. Alright, so the next question deals with metallic bonding, and there's actually two that are going to be on a similar topic. We'll get another one of these later on. So it says, in the band model of metallic bonding, valence atomic orbitals overlap in 3 dimensions, forming bands, molecular orbitals that spread throughout the solid. True or false? So this question here is basically the definition of metallic bonding. So metallic bonding, I should have showed it in 2 dimensions in class. Maybe that was where some of the confusion was. So in metallic bonding, you have, whatever arrangement of the metal ions you have. I showed it in 2 dimensions because that's just easier to draw, where you have this what's called the sea of electrons. So again, that's this sort of delocalized valence electrons. I'm just identifying them as a yellow smear here that goes throughout all the atoms. But this really does occur in 3 dimensions. I drew it in 2 in class, but this, what we call sea of electrons, is really a 3D delocalization of the valence electrons. Alright, so this is kind of the key distinction between metallic bonding and what we talked about earlier in the course, primarily covalent bonding, where we don't just have overlap between 2 adjacent atoms, we have overlap in all 3 directions where there's delocalized electrons going through all the entire structure. Alright, so that's really the picture we want to think about for metallic bonding. It's a 3-dimensional delocalization of valence electrons. There's no localized bonds, there's no directionality to it, it's in all directions equally. So most metal valence atomic orbitals overlap in 3 dimensions, forming bands, molecular orbitals that spread throughout the solid. A little bit more about bands. Remember that bands are going to be basically where we have these sort of groups of molecular orbitals that are primarily bonding and anti-bonding. So we call the lower energy bands the valence bands, and what we call the upper energy ones, which I'll draw in a different color, the conduction bands. So in a metal, these two are right on top of each other. But you have, again, these empty conduction band and the filled valence bands in the ground state. And those are those molecular orbitals that form when you overlap. So why we draw them as bands is because there's a lot of atoms in these structures, so there's a lot of molecular orbitals. And so these molecular orbitals all sort of cluster together into these energy bands that we call them. So really each of these bands would have a lot of energy levels in it really close to each other, as I'm sort of drawing here. And then the conduction band, same thing. You have a lot of energy levels all close to each other. So you get these bands of molecular orbitals that are either filled or unfilled, and that's what we refer to as the band theory or the band structure for extended solids. So this one, then, the answer would be true because everything that's stated here is a correct description of how metallic bonding works. All right, this question here was fun because it required us to think a little bit in more depth about the definitions of crystal structures and unicells. So the unicell in this 2-dimensional crystal contains how many X's and how many O's. So our key here is to try to find what's the smallest piece of the crystal that we can, what's sort of representative unit cell that we can generate this whole pattern, this whole lattice, by translation. There's actually 2 different ways you can do this that will both give you the same answer, but there's a few different ways to think about this, but one thing we could do is let's look at this piece here. So we want to find, again, a piece that we can just take the same piece and then just translate it over and over again. And so if we take this piece here that has X's on the corners and O's in the centers, let's try to do this all in different colors. We can take another one that looks exactly like it that's next to it. I'll do these in alternating red and blue so we can see them better. These are all the same unit cells. So we have those 3 unit cells, X's on the corners, O's in the centers that we can generate. And then if we go in this direction, we have another one that's 4 X's and an O, so the same piece. 4 X's and an O, same piece there. And so remember, the definition of a unit cell is the smallest part of a crystal that can be generated, where you can generate the structure by translation. So if you take this little square here and we just translate it in both directions, across and down, we get this whole pattern of X's and O's that we see here. Alright, so that's our 2-dimensional lattice then that's going to be generated by taking this square unit cell here and moving it in both directions. So if we want to count then, we have, for the X's, those are going to be in each unit cell, again looking at each of these squares here that I've drawn, there's 4 of them, but they're at the corners. And you'll notice that each corner position, for example, that one there, is shared by 4 adjacent unicells. So this is 2-dimensional now, not 3-dimensional. So we just have to look at this plane of the page, and this X, for example, is in between those 4 unicells. We're going to count each of those as a 4th. So in that, we'd have 1 X in the unicell. And then if we go to the O atoms, those, as I've drawn the unicell here, are going to be completely in the center. And so we would have 1 O, but it's in the center of the cell, so it doesn't get shared, so that counts as 1 full atom as well. So there's going to be 1 of each in this unicell. Now there is actually an alternative way you could do this, but you get the same answer. So we could draw, again, instead of putting the X's at the corners, we could put the O's at the corners. So what we could do is do it this way. We'll have this square as 1 unicell, and then alternate again the colors just to see them better. That square is the next unicell, that square there is another unicell, and then if we go in this direction, we have a unicell there, a unicell there, and a unicell there. And if we were to draw this as our lattice, which is a perfectly valid way of doing it, in this case it's sort of ambiguous, what we define as the corners and at the centers, but we would just count these oppositely. So in the second picture here, oxygen would be the one that's 4 times 1/4, or 1, because there's now the oxygens in the corners, each one shared by 4 unicells, and then X's are in the center. So there's 2 ways of counting these, but both ways you get 1 of each, 1 X, 1 O in the 2-dimensional unicell. Alright. Alright, this next question deals with the ordering of boiling points for 4 substances. So the first thing we want to think about is what type of substance it is. So we have KNO3, CH3OH, C2H6, and Ne. We think about what type of substance it is, and more importantly, what type of intermolecular forces are responsible for holding it together. So KNO3 is an ionic compound. It's made up of K plus cations, NO3 minus anions. And so because it's an ionic compound, it has ion-ion electrostatic forces holding it together, and these are going to be the strongest that we possibly have. So anytime we're asked to rank substances in terms of boiling point, remember that the stronger the intermolecular forces, the higher the boiling point is going to be. If you see an ionic compound in your list, that should be the one that you identify as the highest boiling point. So this is the only ionic compound in the list, so it's going to have the highest boiling point. Ionic compounds always have higher boiling points than covalent compounds or other non-metal elements. So for example, this is a covalent compound. C2H6 is covalent, all non-metals in the formula. Neon is not even a compound, it's just a noble gas element. So anything that's an ionic compound, you'd expect to have the highest boiling point. Of all the major structural classes we learned about, ionic compounds as a whole have highest boiling points. For the rest of these to rank them, though, we have to think about the types of intermolecular forces that are present. Again, the stronger intermolecular forces are going to give us higher boiling points. CH3OH has an OH bond. So as we said, whenever you have hydrogen bonded to oxygen, that's one situation where you're going to get hydrogen bonding, which is the strongest of our intermolecular forces. For C2H6, it's a hydrocarbon. This is going to be nonpolar, so you're only going to have London dispersion forces. And then neon is a noble gas. For any noble gas by itself, you also only have London dispersion forces. So 2 of these have the same type of intermolecular force, so if we want to compare these last 2 to figure out which one is stronger, we have to look at the molar masses. So for C2H6, the molar mass is going to be 2 times 12 plus 6, which is 30. And for neon, the molar mass is going to be, from the periodic table, about 20, rounding to the nearest whole number. So generally speaking, if you're comparing London dispersion forces, the one that has the higher molar mass is going to have the stronger London dispersion force. The one that has a lower molar mass is going to have a weaker. Now there's some other things that come into play, like molecular shape, but these are 2 totally different types of substances. We don't really have to worry about the shape, we just have to worry about molar mass. And actually, as it turns out, C2H6, which is more sort of an oval shape, versus neon, which is just these small spherical atoms, this is also going to have a better shape for London dispersion forces. You have a larger sort of surface area of contact. So for really 2 reasons, but molar mass being the more straightforward one, C2H6 has stronger London dispersion forces, neon is weaker, so we expect this one to have a higher boiling point. So basically in these 4 substances, the one with the weakest intermolecular forces is neon, so that's going to have the lowest boiling point. Then you have C2H6, which is still London dispersion forces, but slightly stronger London dispersion forces. CH3OH has hydrogen bonding, so that's significantly stronger than London dispersion, so you'd expect that to have a higher boiling point. And then KNO3, which is an ionic compound, has the strongest forces, ion-ion forces. So anytime you see an ionic compound, you want to rank that highest in terms of really either melting point or boiling point. They're very high for ionic compounds. So this is the correct ordering for these four substances. And we know that neon is a noble gas. C2H6 is also a gas, but it boils at a little bit higher temperature. CH3OH is a liquid, so it's a liquid at room temperature. And then KNO3 is a solid at room temperature, so you even have to go to very high temperatures to melt it, let alone even boil it. So this is the correct order based on our analysis of intermolecular forces. All right, the next few questions are ones that I saw from Blackboard we didn't do as well on, so we can go through these as well. This one also deals with metallic bonding. So we had a true-false question about this earlier, which kind of gave us the definition of metallic bonding. And so, as we said, in metallic bonding you have sort of this three-dimensional delocalization of electrons. You have valence electrons that are just delocalized over the entire structure, not held in place by any two atoms or any group of atoms. It's really pure delocalization. So if we look at these three statements here, in the solid state, metals conduct electricity uniformly in all directions. I didn't specifically mention this in class, but because the bonding in metallic solids is three-dimensional, the conductivity is also the same in all directions. So in other words, the electrons can delocalize uniformly in all directions, which means that the electrical conductivity, the ability for those electrons to move through the solid, is also the same in all directions. So this statement is going to be true. For choice 2, the bonding in most metallic solids is monodirectional. So monodirectional would mean that in a metallic solid you have two metal atoms next to each other, or maybe some group of them, and you have bonds that go in between the two. And this is not true at all. So remember we said that bonding in metallic solids is three-dimensional, so this one's going to be false. So as we said, metallic bonding is in three dimensions, not monodirectional. So monodirectional means in a single direction, but in reality it's three-dimensional metallic bonding. Alright, so choice 2 is one of our incorrect statements, and then for choice 3, the electron C model explains electrical conductivity of metals by assuming that their valence electrons move freely within the lattice. So again, this is sort of that link between the bonding model, the electron C model, which says that electrons are delocalized in all directions, and the fact that electrical conductivity is very high in metals because the electrons can move very freely. So this is, again, a true statement about how bonding in metals works. So you have, as I drew earlier, this picture of metallic bonding, which is just this sort of delocalized smear of electrons. I'm showing it in 2 dimensions here, but in reality it's in all 3 dimensions. And because the electrons are delocalized, you have high electrical conductivity, so that also came into play for a couple of these as well. So the only incorrect statement in this is I meant to circle just that one, number 2, which is that the bonding is monodirectional. Alright, the next two deal with distances along the edges of unit cells. So we did talk about this in class, so I just want to reiterate these points and draw them out. So the first one is dealing with a primitive cubic cell. So in a primitive cubic cell, what we just have is atoms in each corner. So I'm going to try to draw a better cube than that. Just got ahead of myself. Right, so we're going to draw a cubic unit cell, and then in a primitive cell we have atoms in each corner only. Alright, not the best cube in the world, but it'll work. And then we're going to put atoms in each corner of the unit cell for primitive cubic. Now remember, even though we sort of draw them with these spaces in between them, in reality the atoms are going to be in an atomic solid or a metallic solid like we talked about. They're going to be touching along the edges of the unit cell. So if we look at just one face of the unit cell, one square face of this unit cell, which is what we're asking about here, the edge of a unit cell. So this is one square face, and we're going to have all the atoms are going to be sort of arranged in a tight fashion, which I'm not doing a great job of drawing here, probably because this isn't actually a square. So I'm going to try to draw the best square that I can, which is not very good. Alright, so we have that. So that looks like a little bit better of a square. So this is one square face of our unit cell, and then along each corner we're going to have the atoms sort of arranged in this way. Alright, so this is sort of one face of the unit cell, and as we go across one side length here, so from, let's draw this in different colors so you can see it better. So as we go from here to here, we're going to have one atomic radius plus a second atomic radius to get from along one edge from one corner to the other. And so what that means is that along the edge of the unit cell, this distance A that we call the edge length here is equal to 2r in the primitive cubic cell. And that's the answer that we want to pick here. This is, I think, multiple choice, but A is equal to 2r for primitive cubic. So we're not going to ask you about, all of the different geometry aspects of these, but this is a relatively straightforward one, where as we go along one edge of a cubic unit cell, we have 1r plus 1r from to go across the edge. That's a total of 2r for that length there. All right, now if we do face-centered cubic unit cell, we're asking again the same thing. This time the distance across a diagonal face, or what should probably be written as face diagonal more accurately. So it's a little bit weird terminology, diagonal face. It should be face diagonal, really, what we're talking about here. And so if we look at the face-centered cubic unit cell, this one's a little bit harder to draw because there's a lot more atoms in it, but we again have a cube. We have a cube in this case, which I did an okay job of drawing. Then we're going to have atoms in each corner again for the face-centered cubic. Then we're also going to have atoms in the center of each face, which is going to get a little bit crowded here as I try to draw all 6 of them. So that's sort of the arrangement. Now, if we look at it, if we zoom in on one face here of a face-centered cubic unit cell, the picture that we have here is that we have atoms in each corner. We have one in the center of the face, and then another one in the corner like that, and like that. So did an okay job of drawing it, but basically we don't have the atoms touching along the edge anymore, but they do touch along the diagonal, and that's what this is asking about. So if we go across a face diagonal from this corner to this corner, we see what we go through is 1 atomic radius for the corner atom, 2 atomic radiuses for the one in the center. We go completely through that diagonal, and then 1 more to go across this other corner atom in the opposite. So here we're going along a diagonal. They don't touch along the edge in this case, so we don't have as simple of a relationship for the edge distance, but along a diagonal we go through 4 atomic radii. So in this case, the diagonal D is what we're talking about here is equal to 4r. R plus 2r plus r is a total of 4r. Alright, so this ends up with D equals 4r. Again, there would have been a lot of answer choices. This is multiple choice, but you would pick that as the correct one. Alright, so just a couple of things we want you to know about with regards to these geometries and understanding these structures in a little bit more detail that we're sort of asking these 2 questions. Next question is another true-false one. We get less than 50% on this. That's why I want to go over anytime the score in a true-false question is less than 50%. That's a little bit alarming. So here we have atomic solids generally have low melting points, true or false. So remember, we have a few different types of solids. We have, this one's asking about atomic solids. We have metallic solids, which is sort of a classification of atomic solids. So actually, let's do it this way. Let's look at a little bit more detail of the classification. So this is asking about different classifications. This one about atomic solids. So atomic solids sort of consists of 2 major groupings. We have metallic solids, so basically every metal in the periodic table for the most part is a metallic solid. And then we also have network atomic solids. So these are going to be nonmetals that adopt also sort of 3-dimensional structures. So this would be things like network atomic solids is like diamond, silicon, mainly those group 4 elements, carbon, silicon, germanium, that sort of occupy this type of arrangement. Graphite as well, the other form of carbon. So those are your network atomic solids. These are metallic solids, basically all metals. And then other classifications of solids, we have it's sort of a separate category, ionic solids and molecular solids. So we basically have 3 major classifications: atomic solids, which are consisting of just 1 element only, as the name implies, just 1 type of atom; ionic solids and molecular solids, as well as there's also network covalent solids. So a few different categories, and we're going to think about in this case what are the melting points of all of these. Network covalent, which is going to be basically SiO2, sort of another covalent compound that's going to occupy a three-dimensional arrangement. So think about melting points of all of these. It's helpful to remember sort of the ballpark, or at least relative ranges that these fall into. So what you have is, for atomic solids, you have metallic solids, which are going to be moderate to high. I'll write these in red. So the melting point's going to be written in red here so you can see it better. Moderate to high. Network atomic solids, because they have covalent bonding in all three directions, even though they're made up of nonmetals, you have this sort of three-dimensional extended arrangement of covalent bonds, so they're held together very tightly. In graphite in 2 dimensions, and diamond and silicon in all 3 dimensions. So these are also going to have relatively high melting points. So most nonmetals don't have high melting points, but the network atomic solids do, because they have, again, that bonding in all directions. They're not made up of molecules anymore. Ionic solids have very high melting points typically, so they're even higher than metals. Molecular solids are the ones that have low melting points. So these are going to be things like I2, P4, or even polar ones like water, but they only have relatively weak intermolecular forces holding them together, so they have relatively low melting points. Like water, for example, at 0, that's a pretty low melting point compared to most metals and ionic solids, which have melting points of sometimes thousands of degrees. And then network solids also have high melting points, again, because of that three-dimensional arrangement of covalent bonds holding all the atoms together in a very tight, rigid array. So really the only ones that have low melting points on a relative scale are molecular solids. Everything else has, relatively speaking, moderate for metals or high melting points for the network solids, ionic solids. So really, if you're talking about atomic solids, both of those have moderate to high melting points, so this statement would be false. All right, the only type of solid that we classify as having low melting points is going to be molecular solids. Those would be the ones that are considered low. All right, and then the last one here, or no, not the last one, sorry, but 3 more. Last one about solid classification of solids. Which of the following is not a network solid? So basically for network solids, we just have a few examples. So if you can remember all these, then you're not going to have to really worry about many others. So we have group 4 elements. So these are going to be either network atomic or covalent solids. So we have the group 4 elements, carbon, both major forms of carbon, graphite and diamond, silicon, germanium, all will be classified as network solids, as well as SiO2 is another one that's classified as network solid. So those are your major network solids. So if we look at these answer choices here, elemental silicon, Si, that's one of our group 4 elements. Let me go through our table and point that out just so you can see it more clearly. So the group 4 elements, carbon, silicon, germanium, ones that are not metallic, but either non-metal or metalloid, those are classified as network solids. They have that three-dimensional, all of them have that diamond structure, that sp3 tetrahedral arrangement in all directions. So you're going to have elemental silicon is a network solid. Diamond is a network solid with the exact same structure, but with carbon instead of silicon. SiO2 is really our classic example of a network covalent compound. And then graphite is the other major form of carbon. It's not a three-dimensional network solid, but it has two-dimensional sheets that are then held together by intermolecular forces, but it still is considered a network solid. So the only one that's not a network solid here is Buckminster fullerene C60. Now we didn't talk about C60. This is another allotrope of carbon. It's only made up of carbon. Remember, allotropes are different forms of the same element. But this has actually molecules with 60 carbon atoms. And that's why the formula is given as C60. All right. So this is given as C60, which means it's a molecular solid. This would be a molecular solid instead of a network solid. All right. So C60 is made up of molecules that have 60 carbon atoms, and then in the solid phase, it would be held together by weak intermolecular forces, London dispersion forces primarily. So that's considered a molecular solid. One dead giveaway is that network solids, no matter what they are going to be given as an empirical formula. Again, these are three-dimensional sort of infinite structures, so it doesn't make sense to give the full formula. You just give the empirical formula for any network solid. So when we talk about carbon, silicon, germanium, those formulas are just CSIGE. And then you have SiO2, that's the empirical formula for silicon dioxide, even though, again, it's an extended array of silicon and oxygen that goes on forever and ever. But if we see a formula that's given as C60 or the other examples of elements that are polyatomic, like I2, P4, S8, anything that's not written as an empirical formula, we know that these are molecular formulas and these are going to be molecular solids. So that's one sort of clue that you can look at to identify what a molecular solid is if it's not an empirical formula, if it's written as what's clearly a molecular formula, not the smallest whole number ratio, then you can know it's a molecular solid, not one of the other categories. All right. The last two deal with sort of the mathematical equations representing different types of unit cells. We talked about this a little bit earlier in the context of the first question I went over. So this first one here is looking at primitive cubic unit cells, and as we said, in a primitive cubic cell, what you have is just one atom in each corner. And then if we were to extend these cubic cells in all three directions, each corner here would be shared by 8 unit cells. So if we look at the top view of this, so we look at these square faces arranged in a cubic sense, you'd have, this is one of your corner positions, it's shared by the 4 cubes that are below it in the plane below, the 4 that are above, for a total of 8. So in a primitive cubic cell, you have 8 corners filled, but each one is shared by 8 unit cells, so they count as 1/8 each. And that's all you have, which is just going to be a total of 1. So the number of atoms is going to be just 8 times 1/8, which would be choice A there. All right. And then for this next one here, we're dealing with body-centered cubic cell. So in a body-centered cell, it's going to be, in all of the cubic structures, remember that we have all 8 corners are going to be occupied, so that's invariant. But we have, in addition to the 8 corners, in a body-centered cubic cell, as the name implies, we have one directly in the center. Again, a little bit hard to see it in 2 dimensions, but we have one completely at the center of the cube, completely enclosed by the unicell. So when we're counting the number of atoms for the body-centered cubic cell, we have 8 corners that count as 1/8 each. I guess I'm writing it backwards from what the answer choices are, but we can deal with that. So those are the corners. Then we also have 1 in the center, which we count as 1 full atom for that body center position. So that would be choice C here. You have the 8 corners as well, but you also have the 1 in the center, so that's a total of 2 if you wanted to work it out numerically. All right, so that takes us through some of the most difficult questions in this assignment. There are a lot of conceptual things here, so not as much in terms of problem-solving strategies and equations, but a lot in terms of understanding different properties of solids, different aspects of intermolecular forces, and so on. So, definitely read up on this, look through the notes if you have any other questions, and I'd be happy to talk you through any of these as well if anything is still not making sense. All right, so hope the exam goes well for everybody, and I'll see you in class this week.